Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to start in on chapter 15, talking about equilibrium by kind of taking a whole bunch of old ideas and bringing them into a new context. So previously, when we've been looking at equilibrium or trying to figure out what the most favorable combination of reactants and products are, we've looked at this largely in terms of delta G, trying to figure out whether a reaction wants to go forwards or backwards. And we can relate all of this to, again, this equilibrium or this most desired mixture of reactants and products. So again, as we've seen before, if you have a negative delta G or change in Gibbs, this means you're going to want to go forward because molecules are lazy and we're after that lowest energy state. However, sometimes you go a little too far and you have too many products. In this case, we're going to have a positive delta G, meaning we're going up in energy. And this also isn't favorable. And so you're going to tend to want to go backwards. And again, trying to aim for this key point. And the most desired point is when you don't move at all. So there's no change in free energy, meaning you're going to tend to stay exactly where you are. And what we're looking for is the ratio of concentrations where this occurs, where we've gone far enough that we've hit this bottom point, but not so far that it gets more and more unfavorable. And so we're going to be looking at this ratio of concentrations that's going to be referred to as the equilibrium point, and the actual numerical value is going to be the equilibrium constant, because it, as long as you don't change the temperature of the system, the most favorable ratio of concentrations really won't change. And we can give this more or less as the ratio of products over reactants. And we're going to develop the nuances of this much more next time. But let's say we're looking at something like combining copper and tin to change oxidation states. So in this case, we're reducing copper as its oxidation state is going down, and we're oxidizing tin as it's losing electrons. So in this case, we can give the equilibrium constant simply using the ratio of products over reactants. And one of the big things to make note of is that if something shows up in the reaction equation twice, this means we're going to have to raise its concentration to twice the power, because essentially we've generated two of them. And if we're multiplying all the reactants times all the products, well, if it shows up twice, I have to multiply it twice, thus the square. And the real question is, when will we achieve this most ideal point? And so far, we've been looking at equilibrium in terms of favorability, but another good way to look at it is in terms of rate. Because remember, the reaction's always going back and forth, reactants making products, products making reactants. Another common way of talking about when equilibrium is reached is when we're going forward just as much as we're going in reverse. We're just as likely to form products as we are for the products to form reactants. And this gives us an equal state. And so, for example, you can imagine I have a mixture of my reactants of copper tin, and I've got no products. So as I go on, my reactants are consumed and I generate products. And what we're looking for is this point or this ratio of products to reactants. And because I'm consuming 2 copper for every tin, we're going to watch the concentration of copper go down faster than that of tin. And we're going to reach a certain point at which the concentrations really will stop changing. Sometimes it's a little more abrupt, but most of the time you're going to see this slow slope and change, as you'll see a lot of reaction initially and slower down later. And we're going to dive into this concept much later in the semester. However, right now, one of the big things I want to focus in on is that the exact nature of the equilibrium that we reach will actually depend upon our initial states. So if I have a whole bunch of my reactants I put in the system, we're going to have a much different ratio of species than if I start with just products and I'm watching the reverse reaction, as my tin 4 in green goes to my tin 2 in blue. And you're going to see this big change. And because this reaction is going to end up favoring products over reactants, another cool thing ends up happening, that if you actually end up introducing equal amounts of everybody, well, you're still going to end up generating products, but you're going to notice the exact values of species will change drastically based on starting conditions. And that's going to be one of the big focuses of the semester. First, figuring out, will the reaction go forwards or reverse? And then if I know what my initial conditions are, can I figure out where I am? So that's going to be the big feature of this chapter. Next time, we're going to go ahead and look a little bit more at the nuances of our equilibrium constant. Until then, take care.